All right, we're live.
One.
Hey.
Hi.
Let me
All right, let me pull up the hackpad here. All right, shall I officially kick things off?
Sure. Just a moment.
All right. Okay. Hi, everyone. Welcome to meeting number 4 of the Type Theory Study Group. Today we're talking about chapters 5 and 6 of Bob Harper's Practical Foundations for Programming Languages. My name is Danny. I'm an undergraduate at Carnegie Mellon. If you guys want to introduce yourselves.
Sure. I'm Ilan. I'm from Haifa University, also an undergrad.
And I'm Cyrus. I'm a PhD student at Carnegie Mellon.
Nice.
All right. So I think we're going to start off by briefly summarizing what Chapter 5 was about. So Chapter 5 was about dynamics. Cyrus, do you want to talk about this?
So are we starting with 5 or 4?
5, I believe.
Okay. Yeah, let me pull it up. So, I mean, one thing worth saying is that the organization of the book puts the statics first. And,
yeah.
You know, there might be a reason why Bob thinks of languages as first by discussing their type structure and then by discussing the dynamics. But we can start with the dynamics in this case. Maybe get to that. So, I mean, one of the things to point out about dynamics is that there isn't just one way to define the dynamics, right? So you can define the dynamics either as the sort of a transition system, structural dynamics. That's also called in the literature like a structural operational semantics or small step operational semantics. There's various names for that. And then there's also this contextual dynamics, which kind of similar in that there's steps between from one term to another, and you don't define. And then there's also evaluation dynamics, which is like in a later chapter. But
yeah.
Yeah. So those are the 3 forms of dynamics. Do you want me to kind of go into detail about what how each of those work, or what?
Well, I think we can focus on the Plotkin-style structured operational semantics because that's what we're using for like almost the entire book.
Right. Oh, I didn't mention equational dynamics, which are right. So I mean, talking about equations, this is sort of if you go back to like middle school, high school algebra, reducing things by saying when maintaining an equation and simplifying. That's sort of this equational dynamics way of thinking of things. And in a way, all of them are, you can prove these theorems that say they're all equivalent in some sense. So you have to define what that really means. But you could say that,
right.
Contextual dynamics and structural dynamics are equivalent. And I think there's a theorem in there that tells you what exactly that means.
Yes, it is theorem 5.4.
5.4, right?
Yeah.
So, I mean, doing the proof of that is usually a good way to, understand a new form of dynamics. If you understand structural dynamics, you want to understand contextual dynamics, you know that they're equivalent, go ahead and do that proof, and you'll probably understand contextual dynamics after you're done.
Yeah. And so concretely, the way that all of these work in the framework that the book defines is for structured operational semantics, for example, we define a particular judgment that some program steps to some other program, and then we work with that judgment. We sometimes take the transitive closure of it, which means either a program steps once, or it steps many times, or it steps no times at all, and then we use that to model the program running.
So that's the reflexive transitive closure, right?
The reflexive transitive closure. Excuse me.
Yeah, it's actually important that the reflexive be in there, right? Because often what you want to say is that this thing is either already a value or it can, take some number of steps to a value. And if you don't put the reflexive part in there, then you end up with, a weird case when you don't need to take any steps. So
right.
Yeah.
To be careful about reflexivity sometimes.
And talking of values, the other important bit of this dynamics thing is that we define a judgment saying when some program is a value, and then we set things up traditionally so that values are things which do not step anymore. But this is sort of like a meta-theoretic aside that you double check to make sure that you haven't accidentally claimed that something is both a value and like a program that runs similar.
Yeah, and we denote it by the final judgment of states.
Yes. I think throughout the book it's called val, except at the very beginning where he refers to it as final, which is a little.
So that's I mean the stuff at the very beginning of chapter 5 talks about transition systems kind of abstractly. Right. So for the structural dynamics, the final state is only the value state. Or states that are values, yeah. But you could have a you could define a transition system that doesn't look anything like a dynamics or a programming language, and it has things that are final states that are there's no notion of a value perhaps.
I think everyone's favorite example of that is like a vending machine, where you can discuss the various configurations that the vending machine is in, and the transitions are people performing actions on the vending machine.
Right, exactly.
And every time you read a paper on like the pi calculus or something like it, that vending machine example is there at the beginning.
Yeah, I think that's in chapter 30 something where Bob talks about process calculi, I think he calls them. Yeah.
Yeah. All right. So,
we go through the questions.
All right, perfect. So, Cyrus, do you have access to that little hackpad document?
Yeah, I have it up right now.
Okay, great. Then you might be ahead of me. I need to find it.
Okay.
Got it. Okay. So, reading off for the questions for Chapter 5, the first question is, what is a transition system? I think we've kind of been talking about this. A transition system is the combination of that judgment of this steps to that, as well as a couple supplementary judgments like this is a final state, this is an initial state, and is there one more?
Well,
final state, initial state.
This is a state is the first judgment, and then there's initial and final. Yeah.
But for our purposes, a transition system, we really don't have any interest in cases of something being an initial state. It turns out to be trivial for almost everything that we want. Like every program is an initial state, and values are the final states. So usually when we talk about the transition systems that we're interested in, we have this program steps to this program, and this program is a value.
Right.
And I suppose this is a program as a judgment.
Right. So later if we talk about, for example, reference cells, right, then the states are different from the expressions.
Right.
Yeah.
We start talking about stepping like machine configurations instead of just...
So like an expression together with a memory, or expression together with some cache or something like that could be a transition system. So that's why there's a difference between these generic transition systems and then the particular structural dynamics for simple languages that 5.2 is about.
Yeah. And transition sequence is a sequence of transitions that gets us to a final state. Yeah.
Yeah. So a lot of the desirable properties that you can formulate about a transition system, you talk about these sequences of transitions to make the property. So like, it's nice to know that given any one program, while there might be different paths through the transition system, you always end up at a unique final state, which would correspond to a program running to a unique value. That's a nice property to have.
Yeah.
Although there are many interesting programming languages where that's not the case. For example, there's languages that have random number generators that are embedded within the semantics, right? And then each run might produce a different path through the state space.
Yes.
So that's determinism. If we have arrows, many transitions.
Right.
Yeah.
it is kind of nice that determinism, like which is a hand-wavy property that you might say about a programming language, is something that can be formulated very cleanly if you look at it at this level.
Yeah.
Yay, programming languages theory.
Yeah.
So maybe we might get to this in a minute, but actually, if you look carefully at the definition of contextual dynamics, it's not deterministic.
Interesting. How so?
So, do we want to talk about this right now? Yeah.
Sure.
So,
Sounds
I
like
mean, if you look at on page 45, the judgments for determining the what is it called? Replacing the whole with an instruction. These equations 5.7, right? You can always apply You can always apply, for example, for the 5.7b and 5.7c. There's nothing that says that you can't apply 5.7b when E1 is a val.
Yeah.
You
so
just
this is
typically don't. That's her. You know, when you implement it, you choose a particular strategy where you don't.
So this is something that came up a lot when you were defining, when the classical lambda calculus was being developed in like the 30s, 40s, and 50s, that originally the way you defined evaluating one of these programs was you had a big lambda term, and within there were a bunch of points where you could do some work like evaluate an application, and you just said we run a program by picking some random point where we can do some work in evaluating it.
Yeah,
so
exactly.
we built up a surrounding context and did little bits of work, which is what these contextual dynamics are about. And that you would pick some strategy, like you always pick the thing furthest to the left first, or stuff like that.
Yeah, and that actually becomes relevant again when you talk about parallel dynamics. Is, you know, there isn't an order of evaluation sometimes, right?
Right.
You have a parallel pair, you just evaluate both of them simultaneously or in any order that you want. And the understanding is that that means that there's parallelism involved.
And it looks like he uses the judgment E context, so like, which I assume is short for evaluation context, to enforce some notion of determinism in the evaluation dynamics. So if you select out the subset of contexts that force you to only evaluate the right side of a plus when the left side is already a value, then you can regain that notion of determinacy, and you get back that structured operational semantics and the evaluation dynamics are exactly the same.
Right. Yeah.
Nice.
Yeah. So, for example, can we do something like have many holes in the contextual dynamics and have non-determinism that way? For example, we can go both ways in a plus and evaluate them. Something like that. Not enforce the value condition on the first one, and then we get some sort of non-determinism, but still something like the Church-Rosser theorem, that we get in the end to the same thing. Does it make sense?
So,
possible.
Sorry.
Like, what if we don't put the E1 is a value constraint in the last rule? Then we have, I think, many different paths to go.
Yeah. I might have been wrong about E1. Yeah, I don't know if you can always apply 5.7b given rules 5.6.
Yeah, because it requires that E1 is a value. So I think then we must evaluate the first value through 5.7b, and only then we can use C. So we still recover the determinism.
I'm going to push us on to question 3, which is why are structural dynamics defined only on closed terms? I think this one's a little bit of an interesting one because you don't necessarily need to.
Yeah, you don't need to.
Yeah.
You don't. Canonical forms is really the reason why, at least in this book, you define it only on closed terms, right? You want to say that. You know, you want a value judgment, and you want that to be on closed terms, and so you might as well define the stepping judgments also on closed terms.
And this is it's not unreasonable to make this restriction because in practice you really only think about running programs when you don't expect them to get stuck trying to evaluate some value. Like you never run a Java program and leave int x undefined or something.
Yeah.
So it's not an unreasonable restriction to make, and it does simplify some of the theory.
Yeah. In more complicated, for example, independent type systems, you often do end up evaluating open terms. So,
Right.
you know, you have to think very you have to think very carefully about what theorems you want to have, and if it's much easier to just define things on closed terms, then go ahead and do that. That's really why it's only defined on closed terms here.
There is one major trade-off that I'm aware of, which is that if you define certain sorts of realizability models with open versus closed terms, it leads to interesting differences in the resulting theories that you get. This is going way out of left field, but like a lot of the classical type theories based on realizability, like New Pearl or computational type theories, in general, they rely very strongly on the property that you only ever deal with closed terms. And it's a nice, simple sort of universe to live in.
Yeah.
So if we defined it on open terms, would if we run the semantics on an open term, would it be something like inlining and optimizing in inlining constant folding in the compilers or something like that? Because we can't do the operations on the variables that are still unbound, but we can do it on constants, for example, here on integers.
So your set of final states would no longer just be the values. Your final states would include variables, things that include free variables.
So possibly that would be interesting inside the compiler before the program is run, maybe.
Yeah, there's probably some relationship to
open terms and do some optimization this way. I don't know.
Yeah, so I mean, optimization is actually, so that takes us to equational dynamics, right? Optimization is, you find an equivalent term that has maybe a lower cost, according to some notion of cost. There's one given in this chapter, I think. But equational dynamics aren't. There's no sense in which the equational dynamics is defined only on closed terms, and it's also very much not deterministic, because you could always just apply the reflexivity rule in the equational dynamics a million times before doing the evaluation. So, and there's other ways that it's not deterministic as well. So,
there's also no notion of always ending up at a final value, even for normalizing languages with equational dynamics, because you just keep swapping back and forth between two equivalent forms.
Right. Yeah, I mean, the equational dynamics, it's not a transition system. It's an equational.
Yeah. So I've put a question here about equational dynamics, how to make it sort of like a transition system to really evaluate programs with equational dynamics. So maybe some sort of an ordering on terms to decide each step where to go. I don't know, possibly.
Yeah, I mean, you're asking for a decision procedure for equivalence. It's essentially, right? Like
I think if we could explain this really well, then the homotopy type theory people would be quite happy.
Well, so this is definitional equivalence. And there's lots of things that are observationally equivalent that aren't definitionally equivalent. But where I guess he mentions this at the end. He says semantic equivalence, and then chapter 46 is a whole chapter on richer notions of equivalence than given here. So usually when you're talking about like fancy, homotopy type theory kind of arguments, you're not just talking about definitional equivalence.
All right. So let's go to the next question. What is it?
That is a good question. We're skipping all over the place, but this is as good a time as any to talk about 5 or 8, I think. So 5 would be how do we arrive at bylet versus by value versus by name by changing some things in the dynamics, which I think is an interesting question to talk about. Maybe we want to touch on that. So first of all, background to this question. When we talk about programming languages, we can discuss whether their evaluation strategies are by name or by value, so to speak. And the basic intuition is, well, at least where it first came up, is when you're applying a function, do you evaluate the argument before you perform the substitution of the function argument into the body? And this comes up all over the place, but this was like one clear case where we can examine it.
Mm-hmm.
In our language, we have let. So the question becomes, do you evaluate the thing that you're binding in the let before you substitute it in and use it everywhere? If you don't do any evaluation on it, you just substitute immediately, then you're by name. If you do all the evaluation first and then perform the substitution, then you're by value. And there are trade-offs, but pretty much every programming language that you'll encounter is by value. When you bind a variable, it evaluates the thing that you're binding it to. Haskell is a optimized version of a strategy that's supposed to behave kind of like binding. Haskell is a little bit funny, so that sentence gets drawn out. But it's supposed to behave more like by name than by value. And like really old programming languages like Algol 68 were pure, honest to goodness by value, or by name, excuse me.
Mm-hmm.
Interesting.
So it turns out, to wrap up my monologue, that you can change one or two small things in the definition of the operational semantics, and you swap between by value and by name.
Mm-hmm.
So, for example, I think if we drop rule 5.4 that requires E1 to be a value, then we always substitute a let, and then after the substitution, I think it gets evaluated.
Mm-hmm.
Yep.
So, would this be how we would define a by name let?
Exactly. And so
So
you can...
just drop the rule, yeah?
You drop the rule. There's also there's a value premise to the other rule that you drop too.
Yeah. Makes sense.
Mm-hmm. If you want to know how Haskell kind of really does it, there's I think chapter 36 is on by need, which is kind of like by name, except you only evaluate things at most once. So then the dynamics has this like cache for evaluated expressions in it.
Yeah.
So that's if you're interested in kind of how to make by name work kind of more efficiently, like Haskell's compiler does. Chapter 36 is an interesting read.
Yeah.
I should mention that by name has a number of very strange characteristics if you actually decide to implement a language like this. So nowadays, the only place where you really see by name is occasionally some proof assistance will allow you the option of doing by name reduction because there are no side effects and no programs which diverge. But if you have either of those things, then you run into this weird position where evaluating something with all by name causes it to either take an extremely long time and duplicate side effects, or it might terminate, versus with by value, maybe it loops forever or runs much more efficiently. So they behave in very different ways.
Mm-hmm.
So, the classic example is if you have lambda x dot 1, and then you apply that to a program which loops forever, by name, this evaluates to 1. By value, this loops forever. So you can run into some interesting differences.
Mm-hmm. Yeah, in general, the cost of your computation can differ based on whether you do evaluation by value or by name, right?
Yeah.
In particular, if you don't ever use an argument in your function, then it's better to do it by name, right? Because then you won't have evaluated the argument unnecessarily. But that's you would imagine that would be an uncommon case, right? Why even make a function that has an argument if you're never going to refer to it? So.
Also, I think that if we view through programs as proofs, so by name has a strange property that after we reduce, we get a larger proof tree, as opposed to a smaller one.
Mm-hmm.
Well, I think if you look at things proof theoretically, it is by name. Like, you don't have a notion of, like, if you're performing cut elimination, for example, which is our equivalent of substitution, the term gets a lot larger because you essentially copy-paste something in a bunch of different places. So,
it still gets larger with by value too, right? You're still substituting the value in possibly many places.
Right.
There's not really a notion of let proof theoretically, sort of in that sense. I don't have a nice way of stating what I'm thinking, I guess.
Yeah.
All right. So moving us on to the next question here. Another 5 minutes, I think, on dynamics, and then we'll move on to chapter 6. Let's see. We can talk about 8, I think, which is a quick question. So 8 is talking about the fact that the dynamics for our language make use of this plus operator, it seems. And it makes it look like we presuppose the existence of some higher mathematical plus definition when we're defining semantics for our language. But I don't actually think that's the case with what's happening here. It seems like plus is, in fact, a judgment. N1 plus N2 is nat is a ternary judgment with a weird mixed-fix syntax. In which case, this is like a purely judgmentally formulated notion of evaluation.
I think Bob purposely leaves it unclear whether it's a judgment or a meta function that is understood by the reader. You can say in our meta theory we're assuming that there are numbers in the usual mathematical sense, right? The same way, this whole book assumes that there are finite sets of that mean what people generally assume finite sets mean.
Right.
Right. You can define, numbers judgmentally, but you don't necessarily need to.
Or want to.
Yeah. Certainly when you're implementing a compiler, that judgment will be a CPU instruction, not some sort of like search rule based on some judgmental.
Yeah, definitely.
Yeah.
So if we still look at it as a judgment, as you said, as who makes the judgment x plus y? Do we take it as assumptions and for the correctness of our program, or something like that, with the construction of it?
Yeah, you kind of assume that this language is using. It's more that the language is exposing whatever that judgment does.
Right.
And we hope it coincides with our intuition about addition.
We're defining what the language means. So if the judgment doesn't do exactly what we expect, we're not wrong. We've just defined something really silly.
Yeah.
So there's no right or wrong judgments, I guess, in that sense, just things that define really off-base notions.
Yeah. And that actually gets to, at some point you want to say that this is actually addition, but to do that you have to invoke our intuitions about addition. Like at the top of some stack, you're going to have to invoke our notions of intuitive notions of quantity and adding quantities together as things that aren't just judgmental. Yeah.
It's a question of how much you're willing to push into the meta theory and how much you want to explicitly bring to the front. And usually, at least in this book in standard literature, if it's not relevant to the language, it doesn't really make sense to force yourself to define it completely internally.
Right.
Extra pain and source of bugs.
It's the same thing with string concatenation, right? You could certainly define that judgmentally, but it's annoying to do so, and people kind of accept that, okay, string concatenation is just something that intuitively I understand how I would make work, so don't worry about defining it.
Yeah, for example, in dependently typed languages, we usually do define numbers and strings as characters which are sets of some sort of thing. So we kind of do define it internally. So I think this is what kind of confuses me. And where does the x plus y is something come from? Who makes it in the top level? Is it like the CPU that makes the judgment theoretically, right?
Yeah.
Who puts
that
plus line as an axiom?
Well, the language designer did. You can define plus as a function once you have the recursor for natural numbers, which is a later chapter.
Yeah.
But for now, we're not. These aren't natural numbers. They're just numbers that encapsulate a numeral n, and we assume that there's these operations over these numerals, like plus, that we're exposing into our language.
Right. Let's move on, I guess.
All right. How about we take this time to transition to chapter 6? So, Cyrus, we already talked about statics last meeting. This was unfortunately split between two meetings, but now we're going to shift
Oh,
to...
okay, sorry. I didn't.
That's okay. So we're going to shift to type safety now.
Okay.
Does someone who's not me want to introduce this chapter, or should I give a spiel again?
Go for it.
Okay, I give a spiel. So type safety is kind of the basic property of programming languages that we're going to establish throughout this book over and over again. It's our baseline for checking that the programming language that we defined, the operational semantics and the statics for it, are interesting to study, that they kind of mesh together well, and that they don't have any obviously strange quirks. So type safety has a rigorously formulated meaning, and we'll get to that in a second. But the intuition for it is just that there are enough rules in the dynamics, and there are enough constraints in the statics, so that if a program is well typed, we can always discuss how to run it to a value. We never end up in this position where we've sort of fallen out of the realm of programs that we understand. And practically speaking, this generally isn't true in real programming languages. So like C is very famously not type safe. There are all sorts of reasonable programs that are well typed that don't have a defined operational meaning. But even things like Haskell have random things that just take you into strange parts of the language. But when we're studying theory, at least, it's nice to limit ourselves to only studying the nice, clean cases where the statics and the dynamics mesh together and we have fully defined evaluation for well-typed programs.
Well, I mean, it's not just a theory thing. I mean, there are plenty of real-world languages that are type safe in the sense of this book. ML is one, but also, like there's proofs now of JavaScript's type safety and Python's type safety as well, which...
That's true.
Yeah.
That sounds fun.
I should point out that the author of this book, along with Carl Crary, actually formulated a proof that standard ML is type safe. And this is a 30,000 line, 12th development, I believe. It's a very, very large thing. They have formally proven that standard ML, if you stick to the definition, is a completely type safe language.
Although about 3/4 of that is the module systems stuff.
Yeah.
So the actual proof of type safety
I
of
think
core ML is not that huge.
I think there's a lot of elaborating it too. Well, they give elaborative semantics, right? So they spend a lot of time just explaining what each construct of standard ML means in some nice type theory.
Right. Yeah.
And I should also mention that I'm being a little bit unfair when I say that like no real world language is type safe, because a lot of language definitions are type safe, and then some particular implementation attaches some escape hatch or whatever for whatever reason, and then that's the part that doesn't fall within the completely defined realm of type safety.
Yeah, I mean, I guess once you have an FFI into C, then
exactly.
You're not type safe, but...
But at the same time, it's kind of unfair to judge a language based on like the need to have an FFI or something. So maybe I shouldn't do that.
Should also distinguish between memory safety and type safety. People often use the word type safe when they really want to say memory safe.
I want to. Oh, sorry.
That's if like C++ is not memory safe in the sense that you can't rely on having control over the data structure that you think you have control over, right? Because both the stack and the heap are just the only two data structures essentially that exist, and anyone can access them at any location by just doing proper pointer arithmetic. So that's a different notion from type safety. You could conceivably have a type safe but not memory safe language.
I would like to clarify one quick thing that I said, which was a little bit misleading. So I said that type safety is, about a program always being defined for evaluation and like we always know how to run it. This doesn't mean that every program terminates. It just means that you're not going to get into a position where you run the program for n steps and you don't have a value, according to the semantics, but you also are not able to take a step. So it's perfectly type safe to have a program which just steps forever, but it always needs to be able to step. You can't ever get stuck. where you don't have a value, but you cannot take a step. That's
Yeah.
where something becomes non-type safe.
Where you don't have a value and you don't have an error, an explicit error, or I guess what is it called, a checked error.
So if you supplement the
Yeah.
dynamics with a notion of you either have a value and an error as final states of your transition system, then
Right.
type safety is a little bit more complicated to state. But
Yeah, very slightly more complicated. Not very much more complicated.
yeah, extra and or something.
Yeah. So that's if, like, the example here is division, right? If you divide by 0, what happens? You don't want it to just get stuck. You want it to indicate a problem in some way. So you have to supplement your final states with some error judgment and propagate that. But it's okay. That doesn't violate type safety. Type safety is just reformulated to include the error condition.
Exactly.
Error case. Yeah.
So I guess this is as good a time to actually explicitly state what type safety is in like the context of the theory of structured operational semantics that we've been building up. So type safety is a theorem that you'd prove for a language with a judgment E colon tau and a notion of running a program, like E steps D prime. And you would say that if we can say that E has the type tau, then if E evaluates in n steps to E prime, then either E prime is a value or there exists an E double prime so that E prime steps to E double prime. I think this is definition 6 or theorem 6.1, and this is the general form that we always have. Or did I? No, I don't think I got that quite right. They formulate this differently actually than I'm used to. So they have this as a single step, which is interesting.
So you've kind of combined progress and preservation, I think, into one statement.
Oh no, I think they've separated out. Okay, so they've defined type safety as progress and preservation, which I don't think is. Well, I don't know if I would define that as type safety in its full generality. I'm not going to say the book is wrong because that's not going to play out well for me.
I think what you said is a consequence of theorem 6.1.
It is absolutely a consequence. It's
like
just
an immediate consequence of 6.1.
So what I said is a notion of type safety that works for a language where you can't type the intermediate states of evaluation.
Yeah.
So if, like, in the process of running a program, you have to do things where it's, like, no longer makes sense to talk about whether the program is typed properly, then talking about progress and preservation, which is what's given in 6.1, is, like, not a sane thing to do because you can't even explain what one means. But within the framework of languages that we're talking about, we don't have to worry about that. So sorry for the confusion there. The way that we discuss type safety is in terms of two separate notions which are related, called progress and preservation. Cyrus, do you want to explain that one?
Sure. So if you look at theorem 6.1, the first one, it consists of two parts. The first part is called preservation. It says if you have a well-typed term, so E colon T, really there should be a turnstile and an empty context to the left of that, but that's just kind of a notational convenience that Bob likes to use. So if it's a closed well-typed term and it takes a step, then the expression it steps to is also a closed well-typed term. In particular, it has the same type. So it preserves the evaluation preserves the type of the expression. So, yeah, you would expect that, right? You would expect, if my language makes sense, and I say, and 2 plus 2 is a number, and the statics say that 2 plus 2 is going to be a number, it better evaluates to a number. If it turns into a string at some point during evaluation, then what was the point of the type checker telling me it was a number, right? So that's what preservation kind of tells you. Then the second part is progress, and that's this does not get stuck notion, right? So it says if it's a well-typed term, then either I'm done evaluating it, meaning it's a value, or there exists an E prime such that E steps to E prime. So either it's a value or it steps. There aren't any well-typed expressions that are neither values nor can they take a step. Meaning there's no final states other than values.
Yeah.
I
So
guess this is as good as
That's it.
I'm sorry.
Yeah, that's all type safety is.
Yeah.
so type safety tells us that if we have a typed program, it won't get to an undefined state where we don't have anything
Mhm.
we can do. But for example, when we define errors, we tell they are a sort of defined state we can get in the end to. But if we didn't define errors explicitly, then we would get stuck when we want to divide it by 0, because we don't have the judgment
Right.
of the division of 0.
So in 6.3, that's what that talks about. If you write divide 3 by 0, then what should that evaluate to? So there isn't a number that we want to put there, right? Because that would be inconsistent with our intuitions about division. So you add another judgment error, and that's in final state. And then theorem 6.5 is a restatement of progress with an error, the error case also included. So if it's well typed, then either it's an error or it's a value or it steps. There's no fourth case of it being stuck.
Maybe if we reformulate it as the progress property, that either we have a final value or we can step. Then if we just changed errors to be final states too, then it would encompass them too.
Yeah. I mean, you could write it that way, and then the statement of the theorem would be the same. It would be a different theorem, so you couldn't actually just say it's the same theorem. It's a different theorem stated the same way.
Yeah. All right. What else do we have here?
So if we look at the proof of preservation is usually pretty easy. You just look at all your stepping rules and derive a typing derivation for the thing on the right based on premises of the typing derivation on for the thing on the left. That's just an inductive argument. The progress proof is usually a little trickier. Historically, actually, people have had various fun ways of trying to state progress. If you look at the historical notes section at the end of this chapter, it's interesting history there. But the clearest way is by finding this canonical forms lemma that characterizes what the values of each type are. So lemma 6.3 says if E is a value and it's well typed, then if tau is a number, is num, then E is a number, and tau is a string, and E is a string. So you then cite this lemma. This lemma you can prove by induction, and then you cite this lemma in the proof of progress, which is really actually a funny proof. So it's worth doing the proof of progress if you're learning this stuff in like complete detail, because a lot of you're doing it by induction, but a lot of the cases are actually just vacuously true by syntactic contradiction. And that I don't think Bob Plate says that. Maybe he does.
So the canonical forms lemma seems to me like the inversion principle, but on values. That if we have a value, then it must be of some form.
Yeah,
The
it
inversion
is.
lemma
That's what it is.
says
It
that
is an inversion
some
principle.
term, some form, it must have that or some sort of type.
Yeah.
So it's like typing of values, maybe.
Mm-hmm. Yeah, it's not quite inversion if you have more complicated things, because you need that they are well typed, and then usually the canonical forms lemma states not only their form but like the types of the sub expressions.
Right.
This one doesn't need that because none of the values have sub expressions.
Mm-hmm.
Anyway, so both canonical forms and progress, like the proof of canonical forms actually shows this pretty clearly. Like, how do you prove canonical forms? You do induction, and then there's two premises, the eval premise and the e::tau premise. So you're doing kind of simultaneous rule induction on these two sets of rules. But for like all the pairs of rules where the forms don't coincide, you have to, like, if you want to really be complete about it, you have to write. There's a syntactic contradiction, because the first one says that E is of this form, and the second one says it's of this other form, and those can't both be true by syntactic contradiction. And so usually you just skip all those rules, but like if you want to be really explicit about it, it's like an n squared kind of proof, because you're writing a case for each pair of rules in the value judgment and the typing judgment.
Mm-hmm.
Or m times n, not n squared. But. So.
By the way, I have a question. For type preservation, that we always transition to the same type. What if we have dependent types that have some sort of if in the type? Then if we evaluate, we might gain information for which branch of the if we have. So would it still preserve the type, or after we gain more information of some sort during evaluation?
The two types, like the type with the if expression on evaluate and the type with the if expression evaluated, are equivalent. So if you can prove that some term belongs to one and then some term will belong to the other. So you don't really gain any more information in that sense.
I think you're thinking of like a branch of a conditional of some sort might gain some information, but then you're typing just the branch.
Yeah.
Like you don't gain that information.
Oh, I'm sorry. Maybe I misunderstood.
Yeah. Oh, I mean, that's the idea. Yeah. So I mean, you want preservation to hold even in much more complicated settings.
Mm-hmm.
This is a tangent, but now this is bothering me a little bit. Is canonical forms due to the term canonical in this sense? Is this due to Martin Loff? Because this
possibly. I don't actually know.
I would find that kind of interesting, just as
it is
piece of trivia.
I think it's in Martin Loff's like the 1980.
Yeah.
So the history, I think, I mean, so type safety. Milner kind of started this thing with this type programs do not go wrong notion. But Milner's notion of going wrong was explicit. There was actually a judgment that meant this went wrong, and you show that when you have a typing derivation that you never end up in this gone wrong state.
Right.
And then
so there was a.
What's that?
So I was going to say, so there was a formal meaning to this slogan before the internet got a hold of it. That's good to know.
Yeah. And then I guess Wright and Eliason had a paper where they showed that ill-defined states don't arise in a well-typed program. So that became, instead of gone wrong, and do not get stuck, for that notion of stuck that was given in Chapter 5. So that was an explicit, like, kind of like the Milner notion, I guess. I haven't read that paper, so I don't know. But and then it was Martin Loft, which said, okay, if we have this canonical forms thing and we structure things this way, then actually you're never explicitly, talking about stuck states or gone wrong states. You're just showing kind of positively that well-typed programs, there's always a rule in the dynamics for every well-typed program. Meaning that you just haven't forgotten any rules. That's really what proving these things is about, is making sure you didn't forget any of these rules, because there's often a lot of these tedious, search transitions and things that you might forget if you don't. And carefully doing this proof will show you that, oh, I forgot this one.
Mm-hmm.
All right. Have we missed any questions for this chapter?
Let's see.
Can we expect to give us more guarantees?
Such as termination. So there's a question asking whether we can extend type safety to talk about termination.
Well, I mean, the language that we've been working with so far has termination, but that doesn't fall out of the type safety proof. There are languages where you can explicitly write proofs of termination, and then the type checker checks your proof, and then if that falls through, then it's necessarily the case that the thing you prove terminates.
That's interesting. What language, for example?
Oh shoot, I don't know.
That sounds very
Uh,
interesting.
Yeah.
Neutral would require you to provide proofs of termination for certain programs, for example, because it's not decidable.
That's nice.
I think we were chatting about that semi-offline before this meeting started, but that was part of what I was getting at. But yeah, type safety and termination are both notions that you could define about a programming language, and they are often, propositions that you make that you restrict to well-typed terms. But apart from that, they're not really quite the same thing.
So there was an interesting paper at Popple, I think 2013, or one of the relatively recent ones from Penn on a language that has kind of these two modes or something, that one of which terminates and the other one doesn't, and you can talk about non-terminating programs from the terminating fragment. I don't remember who the authors were. Probably should, but you can probably find this on one of the recent Popple. I think it's part of the zombie project, maybe.
Oh, was that Stephanie Wyrick then? I think
she was. Yeah, she was almost certainly on the paper.
Yeah, so that seems like an interesting system for practicality reasons. If we want to prove just write programs, so without providing the proof of termination for, in order to more easily write the program, so we can be in the fragment that doesn't require us to write the proof. But then if we want to get to the more types and more safe fragment, we can provide the proofs.
Yeah. So that was interesting work. You can look that up if that's an interesting topic to you.
Yeah.
Termination is very in right now, I guess.
Yeah, I mean, termination is always kind of tricky. It's in chapter 10 or something when Gödel's T is introduced. There's a discussion of like the pros and cons of having termination. Like there are degenerate cases where the proof of termination is like arbitrarily large compared to the thing you're trying to prove terminates.
Yep.
So if you require that you prove that things are terminating, you can like impose a huge burden on programmers. Where like I know this terminates, but I'm spending a whole day or 2 or 10 proving to the computer, to the type system, that this thing terminates.
Yeah. So, and the last question seems to be, how would we express runtime errors as we did with structural dynamics, but with contextual dynamics? Would it be easier just to say, if this context evaluates to something that has the error judgment, then we are done? Because we specify the main rules for finding the error. We as if duplicated all the rules.
Yeah, that might be the case. I've never actually thought about that. Yeah, I think you're right. The search rules will get rid of all these stupid error propagation rules that clutter up your specifications. Yeah, it's worth writing down to make sure that's actually true. Like write that down and prove the progress.
So, yeah, I guess it would be the advantage of contextual dynamics, maybe.
I mean, that is kind of the point of contextual dynamics, is to like abstract that whole notion of looking through the term for something to do. We just look through the term for an error and pull it up if we find it. So it's nice.
And then we can reuse it,
Yeah.
Does anyone have any closing remarks? I think we're getting to the top of the hour. So.
Yeah. So, what do you think about talking about the next meetings? Because it's been like a month and a half since the last one. So, how would we go about organizing them? What do you think?
So, I think we'll have another email out on the mailing list talking about the 5th meeting. The 5th meeting will be the next 2 chapters. If people are interested in hosting, that would be fantastic to hear. The more hosts that we have up to some reasonable limit makes this a lot more fun and enjoyable for everyone involved. So if you want to get involved, that's great. If not, I guess you'll be hearing from me soon on the mailing list.
Sounds good.
All right.
It might be more. Chapter 7 is on evaluation dynamics, and the point of the chapter is to really show that evaluation dynamics are pretty unwieldy.
Oh, yeah.
Um, so
Okay, so maybe we avoid.
we don't necessarily need to cover it. I mean, I can say something about that right now if people are interested, since it's about dynamics.
Tell you what, why don't you do that, and then we'll see if we'll just go on to chapters 8 and 9 directly.
Yeah, because 8 and 9 are really interesting about, we introduce functions for the first time. Chapter 7 is this kind of interlude where we say, look, in papers sometimes people write these evaluation dynamics or what are called big step semantics for programming languages. And these are kind of sometimes more concise because they tell you exactly how to go from an expression to its value immediately instead of through a sequence of steps. But in fact, proving type safety, it's kind of unclear what type safety even means. So you could certainly prove preservation, meaning the big step that this thing takes preserves the type of the original expression, but there's no clear notion of progress, because progress, it seems to depend on having kind of like a series of computational steps and not just a declaration that somehow we go from this initial expression to this final value. And so if you look at like theorem 7.5, you can kind of like define these goes wrong judgments, which I was just discussing. E question mark, and try to prove that, prove this theorem 7.5 and its corollary, but then you have this question of have you defined enough of these question mark rules, right? And there's no way to tell. You could drop some of them and that theorem would still go through. So it's really quite unwieldy to do big step semantics when you also care about type safety. And so sometimes it's nice to show a big step semantics as an explanatory thing, but like you generally don't want to define your language in terms of the big step semantics because then it's hard to prove that you did it right.
Is there a clear reason why you can't just define an like an error judgment this program diverges and then prove that a well-typed program evaluates to a value according to the big step semantics or diverges? I think that's
there's sometimes you see these like E up arrow meaning E diverges. So that's a proof of you're talking about termination. That's not progress.
No, that would be proving formulation of type safety, which is essentially this program doesn't get stuck, so it either diverges formally or it evaluates to a value.
So do you mean? I think what you mean is actually this E question mark judgment. Diverges means it doesn't terminate, but like, there's also. Okay.
I explicitly am trying to avoid like got stuck. So like.
I see. Yeah.
But being stuck doesn't mean being diverged, I guess.
Yeah.
Because if you diverge, you aren't ever stuck, but you don't ever get to a value.
Yes, that's the judgment that's the notion that up arrow is supposed to capture judgmentally.
I guess.
I think the test is like if you forget one of the big step rules, will proving this theorem catch that problem? And I don't think it will. Because you'd have to forget it and define a corresponding up arrow rule stating that you forgot it.
In any case, big step semantics are sometimes awkward for type safety, and this book does not use big step semantics.
Right.
And if you're willing to suffer through some pain, you can prove that the two notions of semantics, like the reflexive transitive closure of small step operational semantics and big step semantics, are in fact equivalent.
Mm-hmm. Yeah.
All right.
So it's worth knowing that this exists, but I don't think it's worth like going into a lot of discussion about it beyond what we just did. All right.
It was very nice having everyone on.
Yeah.
See you next time.
Yep. Thanks for organizing.
Bye.
Bye.
Yeah.